Hello, everybody, and welcome to your channel Thermal Engineering Concept and Principle. This is Professor Ali Tarat. In this episode and series of different videos, we will talk about an application in the field of thermal engineering, which is the most important application in our heat transfer topic. What are the structural components of shell and tube bundle, heat exchangers, and how do they work? In this series, we will talk about this type of heat exchangers and how can we predict the thermal design of such heat exchangers. Welcome again to your channel Thermal Engineering Concept and Principle. In this episode, we will continue to present what we have started before about thermal design of heat exchangers, especially the shell and the tube heat exchangers. In this episode, we will introduce a complete thermal design of the shell and tube heat exchanger with multiple choices of heat exchanger configurations and specifications. Thank you for your continuous support, and I hope that I will introduce some information that are useful to everyone who works in the field of thermal engineering. From our introduction, we knew that the objectives of the present episode are related to a practical case study from industrial field where a thermal design of heat exchanger is required. And then we will arrive to the summary of the present episode. Practical case study. Let us consider a shell and tube heat exchanger where it is used for cooling down engine oil. It enters the exchanger on the shell side at 60 Celsius and leaves at 40 Celsius. At a flow rate of 5.156 cubic meter per hour, measured at the mean temperature of the oil. On the tube side, cooling tower water is used for the cooling purposes. It enters the heat exchanger at 30 Celsius and returns to the cooling tower at 35 degrees Celsius. Design the heat exchanger according to TEMA standards. We have some information given, or we have to start with these assumptions of physical, geometrical parameters. Let us consider a tube, a stainless steel tube, 316, that is 16 Birmingham wire gauge with outside diameter of 15.88 millimeter and inside diameter of 12.57. The metal thermal conductivity of 16 watt per meter Kelvin, a square tube layout at 90 degree as shown in this diagram, with a tube pitch of 1.25 times the outside diameter as shown in these values. And we have an assumption to choose any of these standard lengths of the heat exchanger, 1.22 meter or 2.44 meter or 3.05 meter, to design this heat exchanger, and select a buffer spacing according to the design requirements, with a buffer cut of 25% at and the fixed tube sheet is selected for this heat exchanger. And finally, we have the water fouling coefficient of 3000 watt per meter square Kelvin. And for engine oil, we have the fouling resistance, that is 0.18 times 10 to power minus 3 meter square Kelvin divided by watt. Here we have the thermal properties of the oil engine and cooling water. These properties were obtained at the mean temperature of the fluid or the bulk temperature, and we are going to use these thermal properties in our design. To start with, we have to calculate the heat load of the heat exchanger from the general form of energy, that m dot Cp delta T. If we substitute the values of the operating conditions of the oil, then we will get the heat load of the heat exchanger to be 50 kilowatt. The next step, we have to calculate the water flow rate that passes through the heat exchanger on the assumption that there is no heat losses and the heat exchanger is well insulated. Then the Q dot oil equal to Q dot water. From that, we may calculate the mass flow rate of water by substituting the values of Cp and delta T to get 8.224 cubic meter per hour. And the next step, we have to move towards the calculation of logarithmic mean temperature. We have delta T1, the end number 1, equal to 25 degrees Celsius, and delta T2 equal to 10. If we use the definition of LMTD, then that will give us a value of 16.37 degrees Celsius. Of course, we have to use delta T mean, which is equal to LMTD times F sub T, and F sub T for single shell, single tube pass equal to 1. That will end delta T mean equal LMTD, which is corresponding to 16.37 Celsius. Let us assume the first trial value of U. Let us start with 600 watt per meter square Kelvin, and that will give us the outside area of the heat exchanger based on the external diameter of the tube. If we substitute the values, then we will get 5.1 meter square. This is the surface area of the heat exchanger, and that will end with the total number of tubes to be about 42 tubes. Of course, we have to calculate then from the knowledge of number of tubes and the layout of a tube in the heat exchanger, we may go and calculate the shell size and the layout specifications. P sub T equal then Um, Tube pitch 1.25 D naught equal to 19.85 millimeter, and equivalent diameter on the shell side for a square layout equal to 1.27 divided by D naught times P sub T square minus 0.785 times D naught square. If we substitute the values, then we will end with a value for the equivalent diameter on the shell side to be 15.68 millimeter. Then we need to estimate the bundle diameter and shell size. D sub B, this is a general equation, has been presented before in many references, and I will put these references at the end of this video. For a single tube pass with a square tube layout, we may use this table number 1, which gives K1 equal 0.25 and N1 equal to 2.207. If we substitute the values in the equation of bundle diameter, we will end with 173.3 millimeter. Of course, we have a clearance between the tube bundle and the inner size of the shell, which can be obtained from this chart. If we use the lower line or curve, which represent the fixed tube sheet, with the use of uh, bundle diameter, then we will end with a value of gamma equal 10 millimeter, and B shell, the inner diameter, to be 183.3 millimeter. We have to select a standard size. If we go to a table 3, which shows that the nearest pipe size can be used as a shell, that is 8-inch pipe, schedule 40S with, of course, this is made of steel. Outside diameter of the shell to be 219.1 millimeter, the inner 202.74 millimeter with a thickness of 8.18 millimeter. And now we have finished that part. Let us go to the calculation of the tube side heat transfer coefficient. Of course, the velocity can be obtained from a general form of the mass flow rate to be 0.44 meter per second, and Reynolds number rho v or u times di divided by dynamic viscosity. Then we will end with a value of 7,192.9. If we apply equation was presented by Tarab, reference 5, uh, in table 2, which will be presented on the next slide, we may get the general form 0.02 Nusselt number equal to 0.02 Reynolds power 0.8 and Prandtl to power 0.5. If we substitute these values for Reynolds and Prandtl, then we will end with Nusselt number to be 55.1. And from the definition of Nusselt number, we may get the heat transfer coefficient on the shell on the tube side to be 2730.9 watt per meter square Kelvin. Turbulent flow correlations. In fact, there are good number of correlations available in the open literature, but I have selected in this table 5 of them, started from Cedar Tat in 1936 until we arrived to Tarad in 2004. All of these correlations are represented uh, in a series of parameters used in these correlations, such as Reynolds number, Prandtl number. And every correlation has its own limitation. It depends on Reynolds number and the Prandtl number. For example, for CDER-TAT correlation in 1936, it is applied for Reynolds number greater or equal to 2300 or less or equal to 10 to power 7. And the Prandtl number should be greater or equal zero point 0.5 within the range to equal or less than 120. And if we go down to the last correlation as presented by Tarat, it is applied for Reynolds number greater or equal to 3000 and less or equal 5 times 10 to power 5. Of course, all of these correlations are applied for turbulent flow conditions. And we have T sub B bulk temperature equal to inlet plus outlet divided by 2 as a mean value. And the film temperature depends on T wall plus T sub B divided by 2. And these correlations, of course, require the knowledge of the thermal properties of these fluids. We are going to use one or two of these correlations in our present application. Because oil as a fluid, the viscosity of oil changes dramatically with the temperature, then we need to include the effect of viscosity on the heat transfer coefficient calculation. To estimate the oil viscosity with the rough estimation, of course, from energy balance, we have uh, A naught, U naught, delta T mean, the overall heat transfer rate equal to the heat transfer rate on the water side. And from this equation, we may get T sub I, the temperature of the inner surface of the tube, is presented in equation number 2. Similarly, we have the overall heat transfer rate corresponds to the conduction heat transfer through the tube wall as presented in equation number 3. And that will give us T naught minus Ti, which represents the temperature difference between the outer and the inner surfaces of the tube. Of course, if we substitute equation number 2 into 4, that will end with T wall, which is equal to T naught, as presented in equation number 5. This equation will be used to roughly estimate the wall temperature of the tube facing the heat transfer to the oil. If we substitute the corresponding values, then we will get that T naught equal 37.9. And if we use the table as shown in table 4, then we will get the kinematic viscosity of oil, density of oil, and if we multiply kinematic viscosity times raw oil, then we will get mu, the dynamic viscosity of oil. And the shell side heat transfer coefficient can be estimated by the assumption that we have a buffer spacing of 200, then cross-sectional area on the shell side corresponds to this equation, and if we substitute the corresponding value, then the cross-sectional flow area will be 0.0081 meters square. That will give us the mass flow velocity on the shell side, that G sub S equal m dot sub s divided by cross-sectional area equal to 153.65 kilogram per meter square second, and U shell equal to 0.1766 meter per second, and that will give the Reynolds number on the shell side G sub S times D equivalent divided by mu equal to 17.09. To continue our thermal design of the heat exchanger with the non-value of Reynolds number, we may use figure number 2 to calculate the heat transfer factor of fluid on the shell side to be 1.7 times 10 to the power minus 1. And Reynolds number will depend on the heat transfer factor, Reynolds number, Prandtl number, and the effect of temperature on the viscosity as designated by the last term to power minus 0.14. And that will end with a value for the Nusselt number on the shell side to be 39.66. And of course, with the definition of Nusselt number, we may get that the oil side heat transfer coefficient to be 359.2 watt per meter square Kelvin. This equation can be used in a general form to estimate the overall heat transfer coefficient depending on the calculated values. If we substitute the values of H naught, HI, fouling effect on the inside, fouling effect on the outside, and the conduction term, then we will end with 1 over U naught equal to 0.00396 meter square Kelvin per watt, and then U naught calculated to be 252.3 watt per meter square Kelvin, which is much less than the assumed value. Therefore, we have to uh, repeat the calculation until we arrive to a value close enough to the assumed value. Of course, these calculations are usually presented in a computerized code, and because it needs many iterations to be used until we get the final uh, approach between the values of the assumed and calculated values. Let us go and continue with a new assumed value. Repeating these calculations many times to reach the closest value. As shown in this table, we have the first estimation for a tube length of 2.44. We have used 5 iterations. Of course, even the buffer spacing was altered to arrive to acceptable values or acceptable percentage deviation between the assumed and calculated values. For example, when we assumed U naught as 250, we has calculated a value of 191.1, which is far from the assumed value. Then we went to 200, we got 178.3. Of course, we have to pay attention for the L sub B, which represents the buffer spacing. It was fixed at 200. Now we went to the same assumed value. We have got 196 with a buffer spacing of 150 millimeter. Then we changed that to 100, I mean the buffer spacing. Then the calculated value was 212.8, and the assumed value 200 is all acceptable because we have got almost 7%, maybe more. We changed the tube length to 3.05 with U 200. We got 185 for buffalo spacing of 200. Then we reduced that to 150, where the calculated value was 200.1, which is equal to the assumed value. Of course, we have to mention here that usually we add almost 10% as for the heat exchanger size as a safety factor. Here's a question. Are there additional heat exchanger designs applicable to this case study? Yes, we have many design configurations, geometries, and all of them fulfill the requirement of the um, heat load of 50 kilowatt per meter square. Uh, uh, sorry, um, uh, 50 kilowatt for this heat exchanger. And then we have a question which version we may use. Of course, the version of the heat exchanger after finishing these calculations depend on the available space on the site, the economic feasibility of using that heat exchanger, the maintenance of that heat exchanger while it is in use, or machining, even machining, and so on. So there are many factors that are affecting the choice of heat exchanger. And if you can just practice what we said in this episode, you may use the same requirements with a selected tube of 3/4 inch stainless steel 316 with outside diameter of 19.05 millimeter and DI 15.75 millimeter in a single tube pass. If you repeat the design, and you may contact me if you need any help to finalize the design of this heat exchanger. Now we have arrived to the final part of this episode, that is the summary. We focused on the thermal design of heat exchanger in a practical case, and we finalized that in a table. You may have a look back at this table and see the differences between the iterations which we have used and how we have manipulated the various parameters affecting the design and how we have arrived to the final stage of this design. We have also some references that could be used to support this video, and you may use them for enriching your knowledge about heat exchangers. And thank you for watching and continuing support. I will see you in the next part of this um, series of episodes about thermal design of heat exchangers. Bye bye.